the room, so thanks everyone. So yes, we're very happy to have Misak Sargsian visiting us this week. He's been a longtime collaborator with some of us and a more recent collaborator on others. Been relying on his calculations on and off since my thesis experiment. Whether it's sort of anything to do with what I consider high energy of the structure of the nucleus, which is different from what everyone else here considers high energy structure of the nucleus. So high momentum nucleons, quark degrees of freedom in a nucleus at rest, and things like that, color transparency and some other exotic effects. And I'm sure we'll hear a bit about some of those, and I'm sure some other new things today.
Thank you very much. Thank you for the opportunity. So I talked today about this short range nuclear dynamics beyond two-nucleon correlations. Let me see. Oh, okay. So just very short introduction, but what is interesting to me. So till now we don't know why nuclei are not collapsing. So even though we know we have nuclei, we don't know why they are stable. I mean, if you ask this question, you say, oh, because we have a nuclear repulsive core. Now, then we say, what is the nuclear repulsive core? It's perhaps originates from repulsion in the NN system and repulsion in 3N and more systems. And then the other question is how we can probe this repulsion, right? To probe this repulsion, we have to probe the nuclei at larger and larger densities, basically. Now, so one way to go and measure nuclei at very large densities is to look at the cores of neutron stars, right? And there is a very interesting developments happening there. I showed this slide like a motivation of the research we are doing. Before 2010, the old observation of typical neutron star was around little bit up 1.4 to 1.5 solar mass. It's above a little bit Chandrasekhar limit, and there were plenty of the models which included strangeness, quark degrees, resonances, hidden color. But then there were also calculations which used purely nucleonic degrees of freedom, adding two-nucleon and three-nucleon correlations, which predicted very hard equation of state that predicted neutron star masses above 2 solar masses. And nobody took it kind of seriously because all the observations were around 1.5 solar masses. And I gave a reference of Pandari Pandey and Heisenberg in the review paper. It's a beautiful review. And so, but then only after 2013, I believe, the first observation came with neutron stars with solar masses above 2 solar masses. And this is a strange observation because initially people thought that if you get a radius below 10 kilometers, then it is kind of signature that we have a quark star at the core. But I think recent observations show that the radiuses are above 12 kilometers, which means that for some strange reason, you squeeze the nuclei and the nucleons, they don't lose their identities. I call it unreasonable persistence of nucleons. It's kind of interesting situation. That means that indeed this repulsion plays a very important role for the equation of state of high density nuclear matter. Now, how you can study this extra on Earth, I mean, in the labs, not in the neutron stars. Nuclear are quantum systems, therefore there are fluctuations. The idea that can you really probe these high density fluctuations where you probe 2 nucleons or 3 nucleons in a distances less than 1 Fermi. So the first question, can we really probe this? Because it's fluctuations that happen at very short time intervals. And initial question was perhaps it's impossible even to observe it. Now, what I will talk today about is white-colored one that I'll show how we identified nucleon-nucleon interaction at short distances in nuclear dynamics. We really probed short distances where the tensor forces are dominant, and we observed very strong isospin effects. That's for two-nucleon correlations, and then I'll go further of these current studies of identification of three-nucleon short-range correlations in nuclei, which like few years ago looked very impossible, but it seems that we are approaching or identifying it. What is the idea? The idea that we know that we more or less know how nucleon-nucleon potentials are from fitting phase shifts. In this picture, I'm showing the only unknown part is perhaps nuclear core. And I took this parameterization from V18. It's the most modern parameterization, but nuclear core, they use the same ansatz of 1960s. That simply tells us that we have no idea how repulsion is generated. Now, QCD gives very interesting perspective what is nuclear repulsion. Is that actually, if you actually squeeze PN system with very short distances, QCD allows to have, first of all, no nucleonic components and 80% of hidden color. What is hidden color is that proton and neutron, and two nucleons, are color octet states, but they combine into the color singlet states. So that's possible. Nothing forbids to have this kind of states, and you calculate simple Krebs-Gordon coefficients, you find out that if I have a 6-quark system, out of this 6-quark, 80% of cases are these hidden color actually states. Now, what we observe in reality, we observe proton and neutron, right? Now, because of quantum mechanics, clearly, if we are observing proton and neutron, and then if reality at short distances have this kind of components, and PN component is only like a few percent of this 100% composition, then you observe that actually if you approach the core effect, it's a quantum orthogonality, because if 90% are not nucleonic states, but you are measuring proton and neutron, you will see that state is orthogonal, and to us it looks like a repulsion, but it's maybe quantum orthogonality. So there is a very interesting thing to investigate to find out if we really approach to these distances, can we really actually see this kind of phenomena which follows from quantum chromodynamics. Now, let me give you a short introduction of how standard nuclear physics work. Even though if we can get all the NN interactions and we sum them up, and we usually use so-called Hartree-Fock potential, this some potential to some Hartree-Fock, where in the Hartree-Fock potential, all individuality or majority of individual properties of NN interactions are lost. And so standard nuclear physics says that you get some mean field of the strong interaction, you calculate the shell structure of the nuclear wave function, but you don't really see like a microscopic structure of NN interaction, right? Now, another approach is so-called ab initio calculations. Ab initio calculations are more or less to the same. You introduce NN and 3N interactions. You calculate, you got very good name, ab initio calculation. Who can argue with it, right? The problem with ab initio calculation that they have little predictive power. Okay, so it's a box, gives you the answer. How the system works, how dynamical effects are dominating, you don't see it. And I will show actually where we say find some effect, we go ab initio calculation, find out it's there, but nobody knew about it. Now, our approach, it's actually phenomenology. What it means phenomenology, I will kind of introduce the concepts. And then the most important thing for any phenomenological approach that you have to verify, you have to predict, make predictions, and it has to be falsified with experimentation. Otherwise, it's not a phenomenology, right? Now, so what we do, our first question conceptually, how we probe nuclei at short nucleon separations. Ideally, let's probe bound nucleons at very large internal moment. So now to probe this, you really need high energy probes to really identify nucleons bound in the nucleus with large momenta. So here comes that you really need high energy nuclear processes to really carry on this kind of studies. What it brings us, so now I'm introducing short theory of high energy electron-nuclear scattering. First, you employ high energy approximations. I've shown that this high energy approximation gives you the small parameter, which is very important in strong interaction physics, because there is no small parameter in strong interaction physics, right? The next, you actually come up with some effective theory, which is a diagrammatic method, which allows you to do calculation using diagrammatic method with effective vertices. So it's an effective diagrammatic method. The advantage of it that you actually end up doing relativistic calculation, because we know Feynman diagrams inherently relativistic. So, but then you have to project it to the light front to kind of suppress so-called vacuum fluctuations that we know that if your momenta is very large, then you cannot really say that this nucleon belongs to the nucleus or it's a product of vacuum fluctuation of nucleon anti-neutron. Same problem that QCD has, right? Now, I will show how light front wave function enters and in the scattering process. And here it's an interesting thing that you define your light front wave function as you observe it. So it is kind of not pre-existing light front wave function that exists somewhere. You probe it. It's a positivism approach. You see what you see, you probe what you probe, and the wave function is the product of your probing. And then, as I said, that actually I show how combining all these approaches, you see how small distance emerges in nuclear dynamics, which allows us to make predictions, which, as I said, you can verify with experimentation. Now about small parameter. It's very shortly I introduced this. So you transfer huge amount of momentum to nucleus, and you probe, say, like you knock out one nucleon with very large momentum, such that now you can combine this quantity Q minus and Q plus, where Q minus is the energy of virtual photon minus its three momentum, divided by energy plus its three momentum. And so then you see that in high energy limit, this is a very small parameter. What you do then, you expand your calculation on order of this small parameter. So theoretically, it allows you to do reliable calculations knowing your errors. Now, if you have a fast nucleon coming out, same thing. You can define minus momentum divided plus component. Again, it's small, and then you can expand it into these small parameters. So it's a very important. That's why all the results that we present, it's all in the domain of high energy nuclear physics, and no such things were observed in say, 90s, 70s in low energy accelerators like Bates, Nikkev, Sargsian, you name it. Now, how effective theory emerges? Let me give you one example, and you will see it. Effective theory emerges with these small parameters in the following way. Consider that you knock out nucleon, which moves in a nucleus. Then actually it interacts with other nucleons, right? Now, what is interesting that there, among all possible interactions, which can be infinite, let's say, or very large, consider a situation that your fast nucleon interacts with one other nucleon, recoil, then interacts with another one, then it interacts back to the initial nucleon. In principle, you can have such an interaction, infinite amount of such interaction. How you are going to write theory. But the beauty of this small parameter, you can show that if momentum of this nucleon is very large, this kind of repetitive interaction with the same nucleon after it interacted with another one and came back and interacted with another one, it's suppressed by this order of small parameter I just showed. Okay? So therefore, what is left is situation that your fast nucleon interacts with one nucleon maybe infinite amount of time, but that's the important thing that if it interacts many times, you take all the sum of infinite interactions and parameterize it with effective vertices, which you can take from the experimentation of fast nucleon interaction with another nucleon. So
is your the remainder of the nuclear is still bound, or just like
It can be bound, it can be free.
and
Depending.
there can also be excitations, right?
Yeah, so it depends what you have at the end, right? You do overlap integral. You're right. It can be bound.
Because you draw it like
free, yeah, just to show it. But the most important thing, that upper part here, that it's a hopeless. It's a large interaction. You cannot say cut it in the first orbit or second, but you can sum them up and replace it with FNN vertices, which is phenomenological experiment. You take it from experiment. Now, once you have this, again, as I said, because of this free parameter, you can formulate effective Feynman rules and do calculation using Feynman rules, basically. But then you have these effective vertices, which you take from experiments, and every other method is you calculating it like you calculating Feynman diagrams. Now, but we know that nuclear physics works with wave functions. How we introduce concept of wave function in these diagrams, right? Now,
and your energy is not high enough that you are not really looking at the deep inelastic scale. Right?
No. It's a nucleon space nucleon. Yes, of course.
Right? So the nucleon still.
Right. It's a nuclear physics. Yeah, you are. Okay. So now about concept of wave function. Why you need to introduce light from wave function? I give you again qualitative description, but it will be clear to you. Say you are here, this red cross, and you are actually measuring your position of other nucleons to build up the wave function, right? Now, what you do, because in non-relativistic case, life is simple, because you measure positions of each nucleus at a given time, right? Because time is universal in non-relativity. It's a Galilean relativity, right? Now, let's go to relativistic case. If I go to relativistic case, each nucleon here, I have to measure at its own time when it's measured, because signal has to come from Z1, from Z2, Z3. Eventually, when you are measuring wave function for each nucleon, you also have to associate a time where you identify this nucleon. So you end up with a wave function of a nucleon with n different times, right? And that's hopeless, meaningless quantity. You cannot deal with this. Now, but then consider that instead of standing here and observing your nucleons, you are riding on the light front and you are observing each nucleon while you are sitting on a light, right? Then what happens that you are on a light front and you measuring actually, first of all, light front coordinates, like Z1, Z2, but then you're also measuring a tau time, which is the difference between T1, Z1, T2, Z2, and you can show that in high energy limit, this tau is identical for each nucleus. Therefore, your wave function is a light front coordinate, longitudinal, and one light front time. It's a beautiful idea. This idea originally belongs to Dirac when he studied kind of mechanics in the light front, but this is used widely in QCD when you introduce light front wave function, right? Partons or quarks. So we do this more or less same with the nucleons. So in some sense, if you want good analogy, consider we doing partonic model that our partons are nucleons. Okay. So I kind of introduce how we introduce this light front wave function in momentum space. It's similar, like partonic model, the nucleons are characterized by momentum fraction, like x's, right, in the parton, and their transverse momentum. So wave function in momentum space will be alpha dependent p perf, and I will discuss this alpha a lot. That's why now I introduce it, like a momentum fraction of nucleons, nuclei carried by the nucleon on the light front. Now, how wave function appears in the following picture. So if I'm actually doing expanding my Feynman diagram into time ordering, I have one where your photon interacts with the nucleon which propagates from nucleus, and this is exactly the wave function because this nucleon belongs to the wave function. But then we have this vacuum diagram where actually what happens that you have fluctuation of vacuum and your photon actually creates nucleon, anti-nucleon, and anti-nucleon absorbs in the nucleon and comes like a final nucleon. But then you are not probing the structure of the nuclei, you are probing a vacuum fluctuation. So that's something which like in finance lecture very well presented. Now, when I go to light front, it's an interesting thing that actually, if I do now projecting Feynman diagram in the light front, I have a normal wave. I go Feynman diagrams and project three terms. One is a light front wave function similar to this. Another vacuum excitation, vacuum diagram or Z graph, and another so-called instantaneous graph. This happens because when you go light front, you the price that you have also so-called instantaneous diagram. What is interesting that you can show that the B diagram, the vacuum fluctuation diagram, is exactly zero if your nucleon has a mass, and the nucleon has a mass, and therefore it's constant. So you end up having two actually diagrams, light front wave function and instantaneous part. And for instantaneous, you do some techniques to incorporate into your light front wave function. It's a treatable thing. So that's the wave function that we operate. Now, next question is where you see this light front wave function in your scattering process. Let me give you another analogy, and you'll see how we do this in a test diagrammatic method. If I go to the Schrodinger wave function, Schrodinger wave function you can transfer to the momentum space, get the Newton-Schwinger equation, and then it's interesting that Newton-Schwinger equation can be expressed through time-ordered diagrammatic method, where you introduce normal Schrodinger wave function as a vertex transition divided by a non-relativistic propagator. We do exactly the same, but now we employ so-called Weinberg equation. It's an equation of bound state or scattering state on light front, where you do tau-ordered diagrammatic method, and you introduce a wave function, which is a transition vertex over the light front propagator. So it's very analogous. And so in scattering process, you know how to identify your wave function. So it's kind of straight. And now I give you an example how I can calculate spectral function on the light front. You apply diagrammatic methods, you introduce the wave function, and you calculate the spectral function. So this is the methodology of our calculation. The next question, how the small distances emerge in our physics. It's interesting that now once I have this diagrammatic method of calculation, I can show that if I write down my wave function of n nucleonic system and look at singular nucleon, which has very large momentum, you find out that the peak of the integral comes in a situation that two nucleons have opposite and equal large momenta. So that corresponds to the actually the large part of your integral when you calculate. But that's not yet two-nucleon correlation, because now you go to the next order, calculate three-nucleon correlation. You find out that your three-nucleon correlations are actually parametrically suppressed. Here it's a second order. I wrote it only if your potential has a form of momentum transfer order of negative n when n is larger than 1. This is why important. It tells us that, for example, in atomic physics, we don't have two-nucleon correlation of electrons and three-nucleon. We should have specific interaction.
So you are doing some kind of expansion now, like
yes,
of scatterings.
Orders of scatterings, and find out that if your potential is short range, you have really two-nucleon correlation. The tree is parametrically small.
And what kind of potential you are using?
This is parameter. Now I come and I use realistic potential, but at the moment I'm saying that why you don't have correlation physics in atomic physics, for example? Electrons, because you have specific requirement for your potential. And we know that
that's the potential you use.
If here I just show that if I use this kind of potential, then I get parametrically small, right? But then in real calculation, I use the realistic potentials which satisfy this condition. Okay? Here I just for simplicity I use this simple form, but in reality NN potential is complicated, but it satisfies this condition. If I fit it Q negative n, n power is larger than 1. Okay? So that's important to me to believe that there should be robust two-nucleon correlation and then small three-nucleon correlation that I can. Okay, so now I can calculate on light front, that's what we do, and assuming that two-nucleon correlations will dominate at large momenta, you can actually calculate any spectral function in high momentum part. saying that it is sensitive to two-nucleon correlations. Now, yeah, I give you an example that we don't really calculate small momentum part because the light front approach is applicable for only high momentum part when you introduce this two-nucleon correlation. Why? Because it's a diagrammatic method for two-nucleon system. I can do calculation. I can do for three-nucleon. But if you have a carbon 12 nucleons, I will never be able to do any meaningful calculation. So that's why this approach works well for two and three-nucleon correlations. Okay, now I told that if it's a phenomenology, it has to be made predictions, it has to be verified or falsified. Now, so we have few results. One, for example, we calculated first simple case with this integration of the neutron, and you guess what? We found actually it doesn't agree with Glauber's theory. It gives you different results, and which was verified at Jefferson Lab experiment. I looked quickly this, and then we predicted nuclear scaling, that you can really identify two-nucleon fluctuations in high-energy experiments, which was actually confirmed experimentally. And then we observed this so-called PN dominance, and we got this high momentum sharing effects. All these predictions, which are actually was confirmed experimentally. So it shows that this approach and the picture we are actually getting maybe correct. Now, new works are this observation that neutron can have new structure that everybody knows it has S and T wave, but we have found that if you go very large internal momenta, neutron may have a new structure, and this new structure only exists if you have non-nucleonic components in the neutron.
Can I have a question? I lost the Schrödinger equation you write down. That's just to solve the wave function for nuclear.
But only for two and three nuclear, not a nuclear. It's a wave function of two-nucleon correlations and three-nucleon.
Yeah, totally. But it's just you look at the wave function of
yes. And then in the scattering process.
But then in the scattering process, you still have to use the wave function, and then you have to also use the measure elements of the proton versus the other proton scattering.
Photon interaction.
And you use the same the potential.
No, you say you have electromagnetic interaction, you have a photon exchange. For nucleon, you have.
Yeah, but that's the vortex. But then you have to go through multiple interaction of this proton. You knock out proton scattering with.
I'm going to show how I did this. Yeah, I calculated, of course.
And I assume you're using the same potential to do that.
No, this is a high momentum scattering. My effective vertex I take from PN scattering.
So you are using different potential for the scattering.
It's not potential, I use amplitude of scattering. If I go back here, I'll explain.
But which is still nucleon-nucleon interaction.
It is nucleon-nucleon interaction, yes. It's taken from experiment. Remember, when I sum it here.
So you are using different things. I mean, you're using amplitude
for wave
for
function.
scattering, but use potential to solve the wave function.
Yeah.
And those are two, in principle, they are sort of related, right?
Yeah, but here, look for wave function. Here I use, like you are saying, potential to calculate wave function, right? Here for this rescattering, I use here I'm discussing like 500 MeV.
Yeah, the momentum exchange is different.
Yeah,
sure.
Here I'm discussing few GeV nucleon interacting with the 500 MeV nucleon. Here I use the PN scattering amplitude.
Okay.
Right. Yeah. If I can use the potential to calculate few GeV nucleon interaction, that's impossible. Okay. Now let me exactly tell this. So the first such approach was we did electroposition of neutron. Indeed, we have two contributions. One, that photon knocks the nucleon out, and this is few GeV. The other nucleon flies without interacting. And the second one, photon knocks the nucleon. We have an interaction vertex. And as I said, we have Feynman diagrams. We do calculations. And this calculation I did when I was a postdoc, and I found that actually everybody knew that in equinal approximation, your peak of scattering should happen at 90 degrees, right? From textbooks, the high energy particle scatters in 90 degrees. It's equinal. But calculations show that actually in this case, because you do relativistic calculation, your recoil nucleon has a momentum. The model called generalized equinal approximation actually peaks not at 90 degrees. It's off from Glauber's prediction. And since there were no experiments, it was very skeptical that this is really right. But in 2008, almost 10 years after this prediction, experiments came, and you see the peak of scattering, you can clearly see it's not at 90 degrees. So actually, what we found that this method works because it's inherently relativistic. It's important. And now, let me show you interesting result. Because of strong anisotropy of fine state interaction, we found that you can get the kinematic window to penetrate inside of neutron and see its high momentum component. Because in the experiments 70s, 80s, when they did in Europe, they found that you don't see internal structure of neutron. All you see fine state interaction. All you see is like a meson exchange. Let me show how it is. At large, these peaks, you really don't probe the wave function, but when you go to specific 25, 45 degrees, you really find state interaction is suppressed, and you can probe internal structure of the neutron. So what we are now claiming that with high energy limit, you really can probe neutron at its internal structure. This is very important if we want to find some quark degrees of freedom in the neutron. Now, let me go to other thing. We're claiming that there are these two-nucleon short-range correlations that happen in short period of time. Again, like think about partonic model, we're looking inclusive scattering from nuclei. In the partonic model, we know that it will be factorized, and that this rho, consider this rho A alpha is like a parton distribution of nucleons in the nuclei. So the partons are nuclei, and then if we claim that that your alpha, momentum fraction, look, momentum fraction is larger than 1. That means that the nucleon carries momentum fraction of correlation more than non-nucleon. Therefore, it should be in a correlation. So prediction was that at this region, 1.3, 1.5, doesn't matter what nucleus you choose, scattering happens from two-nucleon correlation. This is true if you divide cross-section from nuclei to the neutron, you should get the scale, because in the nuclei it happens within two-nucleon correlation. And actually, our calculations again predicted this kind of scaling, which was actually confirmed in 2002. That look at this data are ratio iron to helium-3 and the carbon to helium-3. Better accuracy measurements was John and collaborators in 2011. They found that indeed this scaling is happening. You go this above 1.4 at x are related to alpha, and you find out that actually the ratio is scaling, and the latest, I think it's Barak's measurement, Holby, right? Yeah, and it's kind of confirming different experiments, which is very, very, very cool, actually. Now, why you don't see in small q square? In small q square, this alpha that we can calculate less than 1.3, so you sit in the mean field. There is no two-nucleon correlation to observe. Once you cover 1.3 and up, indeed data shows that it is scaling. So I showed different observation of this scaling. Interesting thing that there is a parameter that you can extract from this scaling. It's called A2, which is a probability to find two-nucleon fluctuations or correlations in nuclei. This parameter depends on nuclear density or A, or depends on asymmetry. So, and it's a hope that if you get this A2 very well, you can extrapolate it, for example, for infinite nuclear matter, and eventually use it for modeling equational state for neutron stars, for example. So that's about A2. Okay, so how much time do I have?
About half an hour.
Oh,
a little under, sorry.
Okay. Okay, so I'm not good. So the other thing which was observed again experimentally, we use this method that I just explained to calculate P2P experiment at Brookhaven. There was AGS, maybe you remember, it was a proton beam on fixed nuclear targets. And this experiment actually again probed P and PP correlation, which our analysis showed that, you know, in a textbook, if you combine PP and PN, there is a linear counting. You find out that you get 4 times more probable PN to be in a pair than PP and NN, just isospin counting. what we observed that actually is not 4 times, but 20 times. So that 20 times you have more PNs than PP correlation. So that was from Brookhaven data. In 2006 and 2008, actually, Jefferson lab did direct measurements, and they kind of confirmed that it's a huge effect of PN dominance. This is state-of-the-art measurement today, and it's an interesting thing that I think it's a Nature paper 2 years ago. They observed that this 20 is actually not. If you go to light nuclei, it's less. Honestly, we don't know why it is less. Why it actually saturates heavy nuclei. I personally believe it's the effect of some partial waves that dominated small nuclei, but that's an interesting observation, requires theoretical explanation. But fact is fact that you get much more PN correlation than PP and NN. Now I explain such an interesting phenomenon. If you remember, in the midfield, you don't see individual property of NN interaction. Now I'm going to say that this experiment proves that you go into heavy nuclei, you see individual properties of NN interaction. Now, what is this? So I focus on 2 interactions, central potential and tensor potential. There is very large central, not large, but there is tensor potential in nuclear forces, right? Now, central potential is huge, but it's negative at large distances, right? Because the binding system. But then it has to cross the zero at some point to become a repulsive core. Phenomenology, we know that central potential has a repulsion. When it crosses zero, being large in all places, when it crosses zero, it becomes small, right? And suddenly gives the opportunity to tensor forces. It's very strange. And the distances we are talking, it's like a 0.8 to 1 Fermi. So why tensor force? Suddenly I bring into discussion, because if I write the central tensor potential for tensor interaction, tensor operator, then you find out that tensor operator acting on PP state gives you 0, on NN state gives you 0, and it doesn't give you 0 only PN state, which has the quantum number of neutron. It's isospeed 0 and speed 1. So this is strange phenomenon. Once you go these distances, tensor force appears, and it selects only PN correlation, this 0.8 to 1 Fermi, and that's what we observe basically. Now I'm coming to ab initio calculation. This is our phenomenology. Once we got this, ab initio people first we say this is nonsense, then they will run their code and they get the same result. And they have this result for 20 years, clearly. But that's I think the benefit of doing phenomenological studies, because it allows you to understand something and then you can check whether this is really correct. So this is a result of ab initio calculation. They indeed see that there is a tensor force that dominates. Now I come to another observation, which kind of prediction observed. But I'll be again very short. So you have the fact that once you go to high momentum in nuclei, it's only coming from proton and neutron. Let me say qualitatively, then what happens that if I go to actually, so we did 2 predictions based on this fact that PN dominates. Let's neglect PP and NN correlation. If you do, then we find out that actually it doesn't matter. If you measure proton and measure neutron at high momentum, they all come from PN correlation. Therefore, if I take their relative fractions, so XP's of relative fraction, multiply their momentum distribution, then for proton and neutron, we have to get the same equality. So it's a scaling relation that a relative fraction times the momentum distribution equals its universal constant, let's say this way. And indeed, it's a constant. It's this probability of APN. And the second property is that momentum distribution itself inverse proportional to their relative fraction. What I am saying qualitatively, if you have asymmetric Fermi system, minority component is more energetic. And so we can really check it. And so the check is actually coming again from ab initio, because we don't have much experiments, but we found that indeed, you see that this is Xn for neutron and for proton, they basically sit on each other. So that's kind of, and then again, our ab initio calculation from for beryllium and 9 and beryllium 10 shows that they really sit on top of each other. So this effect is. And the other thing, which as I said, that probability to find high momentum proton and neutron is such that if one component is minority, so you go neutron-rich nuclei, right? Then we claim that protons are more energetic than neutrons. And then, yeah, ab initio up to for Bohr 11 is confirmed by ab initio calculation. This is very interesting. Look, if you go to iron, according to this, in iron you have more neutron, right? So 27% you have protons above Fermi surface. Only 23% you have neutrons above. When you go to gold, 50% more protons are energetic compared to the neutron. It's a big effect. Now think about neutron star. We have only 8% of protons there, right? So the protons may have very, very high correlation energy. Okay, so this is two papers that measure this effect, and they basically observe this ray that the minority component becomes more energetic, and that's kind of again, this is it's very important for neutron star physics because neutrons are most asymmetric nuclei you can measure. Similar effect is observed also for nuclear matter by collaborators here, and it seems that they see that this is actually so. I will skip the neutron structure, which it's one slide. So I go to the last part of my talk. It's a three-nucleon correlation. Can we really measure now a situation when three nucleons come too close to each other? Now, why it's interesting, for example, I say it's interesting for equation of state. Now, naively, you can take, let's take your K-nex larger than 2, less than 3, and we prove the correlation, because if quark inside the nucleon takes the momentum fraction larger than 2, then it should be at least 3 nucleons there, right? That was the idea. And indeed, first measurement in 2006, this plateau I showed, which is due to two-nucleon correlation, it seems that actually the experiment observed another plateau that attributed to onset of three-nucleon correlation. Because it's the same way if you do nuclear ratios, like in two-nucleon correlation case, you should see new plateau, which will signify that it's a three-nucleon correlation with your K-nex larger than 2. But then there are further experiments actually didn't confirm these measurements. Okay, so you can see that there is any signature that it's actually any new plateau, any new scaling relevant to three-nucleon correlation. But problem here is that actually you have to not discuss the pure K-nex, but you have to discuss alpha. Remember, alpha is a momentum fraction of correlation. The nucleon cares, so this alpha is important. And so, I told you, I showed you this picture that we see scaling in two-nucleon correlation once alpha is larger than 1.3. And so our idea was that let's study this alpha for three-nucleon correlation. So, because question is, what is the alpha for three-nucleon correlation? If it's less, then actually for a given number, then you should not see it. But then the problem to calculate alpha for three-nucleon correlation is to have a configuration, which configuration is dominant. The problem for two-nucleon correlation is back-to-back, right? Two nucleons are correlated. For three-nucleon, you have two extreme possibilities. One, fast nucleon, which is say 700 MeV, is balanced by two 350 MeV nucleons, or they are equally shared. So there are kind 1 and kind 2 three-nucleon correlations, which both can exist. And we focus specifically on inclusive processes, which are used to search for three-nucleon correlations. And we found from analyzing K3 function that for inclusive case, this is a diagram that dominates. The kind 1, that once we know which diagram dominates, because it sits in a small missing energy region, integrated. Once we know it dominates, we are able to calculate alpha 3n for this configuration, which we did. And what we found that actually, in order to probe three-nucleon correlation, you need a condition that alpha 3n is larger than at least 1.6. Why 1.6? 1.6 will correspond to recoil nucleons both have at least 300 MeV momentum. That means they're all three. So the forward is 600, backward is 300. You get central mass momentum 0, but three nucleons are all above Fermi surface. So that's how you build up correlation, right?
I assume this is only the average number, right?
Yeah, but that's where the range where you have.
You should have some distribution of this variable. This average
Yes.
or the.
But the question we say that if you go this range and look at the ratio of different, you have a distribution. But if I look ratio of nuclei to helium-3, for example, I should see the scaling, like for two-nucleon correlation. I should see the constant plateau. So that's our first hope, that once you cross the alpha 3n to 1.6, between 3, it cannot be larger than 3, of course, then you should see the plateau in the ratio of nuclear scattering. So that was the, and then we say, okay, Jefferson lab did lot of measurements at Bjork-NX larger than 2, hoping to see this plateau. But when we redraw this in alpha 3n, we found that quite a tiny part of existing experiments are candidates for looking for three-nucleon correlation. It requires higher Q square to measure it. So that's kind of the problem. And okay, now this is actually the first such attempt for helium-4 to helium-3 when we went to alpha larger than 1.6. And we see some signatures for plateau. This plateau is due to two-nucleon correlation. We know it well. Once you cross this 1.6, it seems that there is a plateau. Now, of course, it's questionable. Errors are large. Experiment not really designed to get good statistics, but this is kind of, very tantalizing indication that maybe it's plateauing. Now, yeah, I mean, I'm not saying you should believe that this is plateau, but it looks promising. Now, if you go other nuclei, it's even worse, right? But it seems that the trend is similar. Again, indicated, but it's not proof. Now, what we do next is the following. We say that let's model what is this three-nucleon correlation. In the first model, in this configuration that I described, we can calculate its structure. That's what we did. And what we did, we found that this three-nucleon correlation in this picture is a result of consecutive two-nucleon short-range correlations. If this is true, and we calculated like a spectral function to this, we found that actually probability of finding three-nucleon correlation is proportional to the square of the probability of finding two-nucleon correlations in the nuclei. Because these two-nucleon correlations will produce effective three nucleons being above the Fermi surface. Give you an idea. So you have three nucleons above Fermi surface. You can make it consecutive two short-range interactions and kick three nucleons above the Fermi surface. If this is true, you expect that your three-nucleon correlation should be proportional to probability of finding two-nucleon correlation in square, because at least two such correlations should contribute. So we did calculations. Observable for three-nucleon correlation, this plateau is a ratio of the nuclear cross-section of helium-3 cross-section in a range of alpha 3n larger than 1.6. Probability of finding three-nucleon correlation, which is the isospin neutral, it's defined through helium-3 and 3-2. And then doing some algebra, we found that probability to find three-nucleon correlation is proportional to square of probability to find two-nucleon correlation in nuclei divided by probability to find two-nucleon correlation in helium-3, and here should be 3-2. Proton in helium-3 and neutron in helium-3, which is proton in 3-2. Now, this language may be very confusing, but let me tell you, after some more calculation, we get very interesting result. We say a ratio of three-nucleon correlation case should be proportional to the ratio of two-nucleon correlation case. Let me tell you this in the picture, then you will see what I am saying. Say you measure this ratio R2, where you know that two-nucleon correlations are dominating. You square it, and it should give you the ratio of three-nucleon correlation case. So that's exactly what I said. You go to the region of alpha 3n between 1.3, 1.5. You measure R2, you square it, and you claim it should be the R3, which is measured between 1.6 and 1.8. And so this relation, which will be the proof that these ratios are three-nucleon correlations. Okay, so these are the lines which are this reflect this relation, and you can clearly say that okay, nothing we prove, but now what we can do, we can average this data into the range of 1.6 to 1.8, averaging into this range, and once we average, we find this interesting result. This is experimental R3, the red, and this black are this R2 square, basically. And we found that the average result is very spectacular, actually, agreement with the prediction that it should be quadratic to the ratio at R2. That's kind of, now we kind of got very excited, and we also studied its A dependence, and we found that actually probability of three-nucleon correlation grows faster with A than two-nucleon, which is important and consistent with the fact that if you go to neutron stars, you should get large effect from three-nucleon correlation. Okay, now this is how, what is the most optimal kinematics to really prove that there is a plateau and you can measure it. But I wanted to finish this into interesting observation of Suji and John is that you can study three-nucleon correlation in three-nucleon systems. So the idea is that take the tritium and helium-3, both are three-nucleon system, calculate the same way the R3, which is now, I define R3 like this, but now consider the A is a tritium. And with the model, with the numbers that we got, we have a clear prediction that if there is a three-nucleon correlation, this quantity should scale to 0.7. So we have a prediction. And so I didn't show the picture because it's preliminary. So they do this analysis and they will be able to tell whether once alpha 3n is larger than given number where we expect three-nucleon correlations dominate, whether this ratio of tritium to helium-3 should scale to 0.7. That could be very nice proof that three-nucleon correlation exists. And last two slides about, I was only focused on this one. The question is, can we study also this one? Why this one is interesting? Because if you do theoretical calculation, you find out that this star configuration is sensitive to non-nucleonic components when you produce delta, and the delta A goes to Ln. And so where you have this genuine so-called irreducible three-nucleon forces that become important. Now, what we found that the only sensitivity that you can have if you have three-body breakup reaction of helium-3 at large Q squared. It's a very expensive experiment. So you take the electron, you scatter helium-3, and you measure all three, measure scattered electron and two nucleons, third is measured, but then you can get huge sensitivity of three-nucleon forces. So I believe this is experiment of future because this, if three-nucleon correlations will be observed in inclusive processes, maybe this is where to go next. Okay, so my summary is that you should proper variable for describing correlations, light from momentum fractions. The signatures are scalings or plateaus for 2n and 3n. And then the prediction is that the plateau at 3n should be equal to the square of the plateau at 2n, which is important. And kinematically very unambiguous verification that there are correlations to go to higher Q square. And for 3n forces, I just told that you need exclusive processes. Okay.
Yes, I would have said you should feel free to put in the plot as long as it's just here, but yes, that.
So actually, what they see that the ratio goes up in 3-2, and then you expect it stays there, it goes down, the approaches.
You went too fast. What's the definition of the alpha 3 in terms of experimental variable?
Alpha 3n?
Yeah.
So yeah, so we say it should be larger than 1.6.
I know. What's your definition?
Oh, alpha 3n is a momentum fraction of the
It looks like you plotted the data as function of alpha 3n.
Yeah,
So it must be some kind of
yeah,
how to define in terms of experimental variable. What is it?
yeah, I calculated, I consider, let me go here.
Because you went very fast.
Yeah, it's here. So how I calculate, I consider scattering of visual photon on three-nucleon system. Where at the end I have actually in this three-nucleon system, I have a fast proton, and PS is sum of these two momenta. So I have this configuration.
So you have in experiment you have to measure all the momentum of three-nucleon.
No, because what I said, so I'm scattering of one nucleon.
Yeah.
Two are recoil nucleons.
Okay.
So the minimal thing which I require, the two recoil nucleons fly parallel, opposite to the first one, and balance its momentum, right? And then I do my kinematic algebra and calculate light front momentum fraction of this three-nucleon system.
That's the variable you define.
Yeah, now I got variables. Q minus, it's a photon energy minus photon momentum. These are nucleon masses. W3n is a mass produced on three-nucleon system, which you know. And MS is the mass of this recoil two-nucleon system, which I put two mass on nucleon, minimal possible variable. It can be larger, but it's minimal. And so if you look at here, every variable is known here. So they know W3n, they know Q minus.
So that you have to measure, like you have to know the sort of sample mass of the remaining two-nucleon.
Yeah, I took it like a two-nucleon mass. I assume the recoil nucleon is two-nucleon mass. W3 and how much mass I created is three nucleons.
So maybe I'll explain that the nomenclature. If you wanted to reconstruct alpha, yes, you need all of the final state nucleons as well. If you're striking one nucleon and you assume the A-1 system comes out coherently, then under that assumption you can calculate alpha. Or you can assume that it's a two-nucleon correlation, and then you can model the system. So alpha 2n is our best guess at alpha, assuming it's a two-nucleon
physically,
correlation.
what is the alpha 3n is what is physically interpretation? What is it?
It's a momentum fraction of three-nucleon correlation carried by the struck nucleon PM. So that how much I have this three-nucleon system, what is the momentum fraction of this three-nucleon system? This PM carries.
PM what?
This nucleon, knockout nucleon carries.
Okay.
If it's larger than 2, clearly it should be three-nucleon correlation, right? But then we have this 1.6 because we believe that already 1.6, this configuration should dominate. Ideally, once it's larger than 2, you always have you should have a three-nucleon correlation because you cannot have momentum fraction larger than 2. That means at least three nucleons should be involved in the process, right? Like so that's like if I talk about Bjork-N-X larger than 1, that means that you have at least 2 nucleons involved in the process, right? Independent elastic. You cannot have Bjork-N-X larger than 1 on proton, but you can have on neutron, right? Because it's the same logic. So yeah, it assumes that the recoil is a coherent, of course, but it gives you an idea where to look at them.
Can I ask a question about the point with the averaging of the data points in the plateau?
You mean here, right? Here.
Yeah.
Yes, so you see we had the alpha 3 and 1.6 and up. And so these lines are prediction that you measure this line here, two-nucleon correlation plateau.
So the lines
you square it.
Are the lines to the two plateau, are they a fit to these data points?
Look, so I measured this, I fit here like a plateau at two-nucleon correlation. I got this black line.
Yeah.
That's a R2.
Okay.
I square it, I made it here R3.
And then it's supposed to have an error band in it, it's just very small, or?
It's a very small, it's
Okay.
like, consider that, yeah, it's fitted, it's one number, yeah. Of course it has to,
Are the correlations between the data points taken into consideration in this fit, or is it?
this is good question, I don't know the answer, I'm theoretical thesis. But this is, you know Donald Day, right? So we did the paper with him. So he maybe Joe can answer.
In general, yeah, so with these extractions of A2, when they're quoted with an uncertainty, they're taking into account the correlations at least as well as they can be understood.
Okay.
I don't know, since this was a separate analysis, it might not have, but we also quote the errors in a way that if you aren't careful about it, you still get something reasonable.
That's interesting.
So now what we do? This picture tells you nothing, right? And it's correct. So what we did, we average points above 1.6.
Okay.
We also averaged here these 4 or 5 points, which is for R2. So we got average R2, average R3,
Okay.
and we plotted here.
So I guess I have again the same question. Is it correlated average or is it just an average? Or you're not sure.
Just the average.
I think it's just simple average, yeah.
Actually, I think here, the errors would be, if they weren't including the normalization uncertainty that affects all points, the A2 error bars, I think, would be invisible. So I think it must be including it.
Okay. It's just that the purple data points seem to be quite higher than the purple line in the previous plot. So I was a little confused about how,
You mean here?
a little further down, so the purple triangles,
Uh-huh,
so they're
yeah,
like the 3 that I can see
I
are
understand,
much
yeah.
higher than the lines.
The
Or I
fourth-
mean, they're
The fourth
upper.
looks like it's covered up by the circle below and is much lower.
Okay.
There's
And it
another.
has a smaller error bar, okay, so that's probably.
But I believe he, when he averaged, he weighted by errors
Yeah.
too, right? So.
Okay, thank you very much.
And out there, it's all statistics, so for the A3, it doesn't matter too much if you neglect correlations, because
You
the
know,
statistical errors are
In
so
the
large.
paper, we didn't claim that we observed nuclear correlation. We were careful and then of course the trees were unhappy that we wanted to claim such a thing, right? Because errors are large. But the idea that it's very intriguing that you get this quadratic because it's a big change. So it's quadratic.
If we're done with the 3, I had a question about the earlier parts of your talk, where you said that the deuteron has a significant delta component.
Once you cross around 750.
So a question then would be, if you looked at deuteron photodissociation at large Q squared, would you start to see a lot of events with delta?
We always thought that this experiment should be done, and it was perhaps very difficult to do. But we have different observation, which is very intriguing. Jefferson lab measured neutron disintegration that goes to proton and neutron.
Mm-hmm.
And once they cross 800 MeV internal momentum, the data overshoot any theory which uses standard neutron waveforms. So there is something there which is significantly important once you cross 800 MeV. But you are right, but this is a very challenging experiment, how you measure delta. But yeah.
And they did look at what could be done in detail at 6 GeV in class and decided we didn't have the reach to do it well.
Mm-hmm.
It was examined again at 12 GeV, and I don't remember the details, but actually Shuji talked with the Bunker at Michigan State who had been looking at it. So if you're interested in following up after, she probably has a better idea of what's possible or not.
You know, with this paper which we published in PRL, we did following thing. What is neutron? If you don't know, really you know one thing, it's a composite system and it's a pseudo vector, right? And we approach this way like a paradigm shift. It's not the SD component, it's a pseudo vector composite. And then we wrote the all possible vertices that neutron can have. And when we did high energy approximation, we found that there is a new structure, this new structure, which is not zero at high energy limit. But then we also proved that this structure only can exist if it's not a proton and neutron, something else other than neutron. So we're now very hopeful that this enhancement that they see may be relevant to. For example, this can be from hidden color or from delta data.
So if you have quark exchange, could it be delta plus plus delta minus, or would it only be delta plus delta 0?
It enters with different
Quark coefficient.
Right.
Okay.
In fact, we have to predict the relative rate of the production.
Can I ask about the irreducible three-body force towards the end? If I understood you right, and maybe I didn't, you said that only if I look at this triangling process, am I sensitive to that?
You are most sensitive in this, because in this case, excitation energies involved is large, missing energy of excitation. Where you expect that in the first instance of interact, you can excite one delta n, and the delta with the second instance, delta n goes to nn. Yeah, but we found that this, theoretical calculation shows that this is the configuration where irreducible.
So where the momenta are equally distributed.
Yes.
But you have also, of course, a two-body contribution to that. Right?
What we did, there is also, of course,
Right.
but this is very, that's why we can do calculation with and without these three forces, and see the huge difference if you isolate this configuration.
Okay.
If I look at the inclusive scattering, I don't see much.
Right. Okay.
Any other questions? All right, now let's thank you, Misak again.